The charge carriers in a metal undergo random thermal motions, but there is no net motion. So if we take a conductor having a sea of electrons, those electrons are bopping about, randomly moving, but because the collisions are random, if you were to track one particular electron, on a whole, on average, that electron's net displacement will be zero due to all of the random motions, the random collisions that it'll experience. Now, the speeds of random thermal motion are extremely fast, on the order of 1 million meters per second. So if you were to follow that single electron is going to be moving at about 1% the speed of light. That's extremely fast, 10 to the 6th meters per second. But even though it's moving extremely fast, the random motion results in about zero net displacement of the charge carriers. So that single electron doesn't really move very far if you look at its net motion, approximately zero. Now, if we establish a potential difference, remember, establishing a potential difference means that we're going to have a non-zero electric field throughout that conductor. So charge carriers throughout the volume of a conductor drift in a net direction in response to a potential difference in non-zero electric field. So even though we have a large number of random motions, with the presence of that electric field, that gives a net direction for those charge carriers to move. So despite their continued random motion, positive charge carriers will drift in the net direction of an established electric field, while negative charge carriers, as depicted in this diagram, will drift in the opposite the direction of the established electric field. We can call the magnitude of the average velocity in which these charge carriers move, we will call that the drift speed. And the drift speed is just defined as the displacement along the electric field per the time it takes to undergo that displacement. More specifically, drift speed is the average speed in which charge carriers move through a displacement delta x between collisions in a time interval delta t. Now, it can be shown that since these charge carriers are moving in response to the established electric field, and the electric field creates an electric force on each of our charge carriers, the drift speed is directly proportional to the magnitude of the electric field, where the proportion is given by the charge of our charge carrier, in this case the electron, tau, which is defined as the mean time between collisions in the material, per the mass of charge carrier. So in this case, it would be the mass of an electron if we are looking at the charge carriers and conductors. Suppose that there's a wire of cross-sectional area A and having a number density Ne consisting of n number of conduction electrons per unit volume, where the electrons move a distance along the wire delta x in time interval delta t. It can be shown that the electron current in this wire may be expressed in terms of the drift speed, v of d, given by I equals the number density times the area, the cross-sectional area through which those charge carriers are moving, times the drift speed of the charge carriers. Well, let's go ahead and see how we would show this. Let's take a wire of cross-sectional area A. And let's say this wire has a certain number of electrons per unit volume, that's going to be our number density. And that number density is the number of electrons given per unit volume. So let's look at these electrons as it travels a certain distance d, or rather delta x, along the length of our wire. And let's say it travels that distance delta x in a time interval of delta t. Well, those charges, remember, we defined electron current to be the number of charge carriers crossing a point per unit time. So if we have n number of charge carriers per unit volume, and we know the density of charge carriers in the material, in this case, that density could be looked up if it's a conductor. So in this case, we will have the number density times the volume. Well, if we take a volume of these charges, that is going to be equal to the area times the distance it moved through. So that's basically the volume of a cylinder as I've depicted in this picture, but it's essentially the area times the displacement. So with that said, we could say the number of charges then is equal to the area times the displacement times the density of charge carriers that we have. This means that we could express the electron current as the number density of charges times the cross-sectional area those charges move through times the displacement divided by the time interval in which those charge carriers move. Well, notice that the displacement over the time interval is what we defined as our drift speed. So this means that the electron current can be expressed as the density of charge carriers in our material times the cross-sectional area through which those charge carriers move times the drift speed. Here is an alternative expression for electron current. Notice this electron current is directly proportional to the area of our wire. So the greater the area, the greater the current. And that makes sense because that means there are a larger number of particles that can cross that cross-sectional area. And then it also means the greater the drift speed of our particles, the greater the electron current, the greater the number of charge carriers crossing that cross-sectional area per unit time. Here is a subtle distinction in words. Electric current as opposed to electron current. Electric current is the net movement of charge carriers through a cross-sectional area, and that's defined as the time rate of change of charge. So remember, if we have a total number of charge equal to n times the value of the charge carrier, we're going to define current to be that time rate of change of the total number of charge. So that is d dt of our number of charges times our value of our charge per charge carrier. And this ends up just being equal to the value of the charge times the electron current. So in other words, current is equal to the value of the magnitude of the charge of a charge carrier times the electron current of our particular material. Whereas electron current is the number of charges crossing a point per unit time, Electric current is directly proportional to that number of charges crossing per unit time. And the proportionality constant is just the magnitude of the charge of each of our charge carriers.